Hello students and friends. In this video I'm going to talk about optical isomerism, which is an important topic. It comes under stereoisomerism in organic chemistry, and as you know that when you talk about stereoisomerism, it has to do with the three-dimensional arrangement of the atoms in a molecule. So we find that sometimes the two-dimensional arrangement of the two molecules may be the same, but they may differ with respect to their three-dimensional arrangement. That means the atoms are arranged in a different way in three-dimensional space. Now, within stereoisomerism, we have optical isomerism. So as soon as you hear the word optical, it reminds you of light. So optical has to do with light. So obviously a question can come in your mind that light basically is a concept in physics. So why we are talking about light in chemistry? Yes, the reason is that we are studying the property of the molecules with respect to their properties with regard to how they behave when light is passed through them. So that's why we have to study optical isomerism in organic chemistry. Now, because it has to do with light and it has to do with physics, we don't have to actually go into too much depth of the nature of light, which we do in physics, but basically we have to know some very basic ideas that light is actually a wave phenomena. Actually, it is also a particle phenomena, but here we have to deal with the wave nature of light. And light, is an electromagnetic wave. But once again, you don't have to actually bother about the electromagnetism aspect of the light. Basically, you have to understand that the vibrations which comprise light are electromagnetic vibrations. And when you consider uh, an ordinary light, and particularly if you consider the monochromatic light, which is the light of a single color, then the ordinary light is unpolarized, which means that these electromagnetic vibrations can occur in many different directions, and each of these directions is perpendicular to the direction in which the wave is traveling. So for example, if the wave is traveling, the light is traveling in this direction, then the vibrations, the electromagnetic vibrations, can be in so many planes which are perpendicular to this direction. It can be this, and if you look in three dimensions, it can be another plane like this, or it can be another plane like this. So there can be various planes which are all perpendicular to the direction in which the light is traveling, and that is the unpolarized light. But we have to actually convert this ordinary light, monochromatic unpolarized light, into the polarized or the plane polarized light. Now the plane polarized light is simply the ray of light in which the vibrations are only in a single plane. See, only in a single plane. That means we need to use some material which can convert the unpolarized light into polarized light, and one such thing is a Polaroid sheet. As you can see that using a Polaroid sheet, you can see that it can be like a number of vertical slits. So when these vibrations pass through the Polaroid, so many vibrations cannot pass through it because of the barrier, and only those vibrations which are aligned with the slits can pass through it. So in this way, the light which emerges out from the polarized sheet consists of vibrations only in a single plane, and hence it is polarized light. Now, why do we need polarized light? Because we have to study the property of the molecules as to what happens when this polarized light passes through a sample which is contained in this tube. So what we find is that the direction of the plane gets rotated, and that can be understood if you use another Polaroid, which is the call is the analyzer, and if you observe it with the eye, then only you can understand that how much, by how many degrees you have to rotate the analyzer so that you can again see the light that passed through the first polarizer, because again they should be aligned with respect to each other. So in this way, you can understand that the molecule which was taken in this tube has been able to rotate the plane of the polarized light. Now it is obvious that why the light that we use should be in only in one direction, because if it were in so many directions, then we would not have been able to understand that the light got rotated, because there were so many directions in which it was already vibrating before entering the tube. But because it is vibrating in only a single plane, it is easy to identify whether this plane has been rotated or not rotated. And if this rotation takes place, then we say that the substance taken over here is optically active. And if there was no rotation, then it means that the sample was optically inactive. Now it has been found that in order for this organic molecule to be optically active, it must contain a chiral carbon. That means this carbon should be joined to 4 different groups. So actually, if you see this, if you look at this particular formula, this molecule, then if you look at this particular carbon, then it is joined, this is actually tartaric acid, and it is joined to OH, the H, the COOH, and the CHOH. This whole thing is considered as one single group. So there are 4 different groups joined to this carbon, and this carbon is therefore called as a chiral carbon. And only if a chiral carbon is present, then only the compound can show this optical activity. That means it can rotate the direction of the plane polarized light. If this chiral carbon is not there, then that compound will not show any optical activity. And another thing to understand is that if you have a chiral carbon, then its mirror image is non-superimposable, and that I have shown in another video what is the meaning of non-superimposability, that you can watch. So when they are non-superimposable, the mirror images are not superimposable, then these are called as enantiomers. And the property of the enantiomers is that they rotate the light in different directions. So if the direction in which they rotate is towards the right, it is indicated by a plus sign, and if it is to the left, it is indicated by a minus sign. If the concentration of these two enantiomers is the same, then they will rotate by the same amount of angle also, that is plus 60 in this case and minus 60, if the concentration of each one is the same, and under specific conditions. And if you mix these two isomers in equal amounts, then you know that it is called as a racemic mixture, because then the rotations get cancelled out and then there is no optical activity seen. Now, the question that comes in the minds of the students is that what is the importance of studying this property, that we have enantiomers and we have chiral carbons and non-superimposable images. The importance of this is actually in biochemistry, and it has been found that out of these two enantiomers, like which are mirror images, which are appearing to be very similar, but still they are different. One of the enantiomers, one of the mirror images or one of the molecules may be active in your body, and the other isomer, even though it is so similar, may be absolutely inactive or harmful inside your body. And the reason for that is that even the enzymes in your body are three-dimensional structures, and therefore they will be compatible with one of the molecules but not compatible with the other molecule. So the pharmacists have to understand this property when they manufacture the different drugs for treating different diseases. So hope you understood this, and we will discuss this property once again in some other video. Thanks for watching, and if you like this video, please give it a like and subscribe to my channel and share this video with your friends. Thanks a lot for watching.